Electromagnetic waves such as light are generated by the vibration, energy transformation, of electrically charged particles. These waves are characterized by their oscillating electric and magnetic fields, which move perpendicular to each other and the direction of wave propagation. Discovered by James Clerk Maxwell and verified later by Heinrich Hertz, these waves propagate at the speed of light, carrying energy and information across a wide spectrum of wavelengths from radio waves to gamma rays. Electromagnetic waves are unique as they can travel through a vacuum, unlike sound waves. They play a vital role in natural phenomena as well as in numerous technologies. Characteristics of electromagnetic waves. Electromagnetic waves exhibit several key characteristics that define their behavior and interactions. Transverse waves. They are transverse, meaning their oscillations of electric and magnetic fields are perpendicular to the direction of wave propagation. Wavelength and frequency. Each wave has a specific wavelength, distance between successive peaks, and frequency, number of oscillations per second, which are inversely related. Speed. In a vacuum, all electromagnetic waves travel at the same speed, approximately equal to the speed of light. Energy. The energy of an electromagnetic wave is directly proportional to its frequency. Higher frequency waves like X-rays and gamma rays carry more energy than lower frequency waves like radio waves. No medium required. Unlike mechanical waves, electromagnetic waves do not require a medium to travel and can propagate through the vacuum of space. Spectrum. The electromagnetic spectrum encompasses a wide range of wavelengths and frequencies, from very long radio waves to very short gamma rays. Reflection, refraction, and diffraction. Electromagnetic waves can be reflected, refracted, bent, and diffracted, spread out, similar to waves in water. Polarization. These waves can be polarized, meaning the orientation of their electric field can be aligned in a particular direction. Interaction with matter. Electromagnetic waves can interact with matter in various ways, including absorption, transmission, and scattering, depending on the nature of the material and the wavelength of the wave. Duality. Electromagnetic radiation exhibits both wave-like and particle-like properties, wave-particle duality, behaving as photons in certain situations. Electromagnetic spectrum. The electromagnetic spectrum is a continuum of all electromagnetic waves arranged according to frequency or wavelength. It is fundamental to understanding how energy is transmitted across space. The spectrum is a crucial tool in various scientific fields, aiding in the study of atomic and molecular structures, astronomical phenomena, and various forms of communication and imaging technology. Types. These waves vary greatly in their properties and are categorized into different types. Radio waves, microwaves, infrared waves, visible light, ultraviolet lights, X-rays, gamma rays, radio waves. Radio waves are generated by charged particles undergoing acceleration, such as electrons in an antenna. When these particles accelerate, they create oscillating electric and magnetic fields, which propagate outward at the speed of light. Features. Long wavelengths. Radio waves have the longest wavelengths in the electromagnetic spectrum, ranging from about 1 millimeter to 100 kilometers. Low frequency. Their frequencies are the lowest among electromagnetic waves, spanning from about 3 kHz to 300 GHz. Non-ionizing. They are non-ionizing, meaning they don't carry enough energy to ionize atoms or molecules, making them safer for long-term exposure. Penetration ability. Radio waves can penetrate through various materials, making them ideal for communication. Propagation. They can travel long distances and propagate through the atmosphere, reflecting off the ionosphere for extended reach. Applications. Broadcasting. Used in radio and television broadcasting, transmitting audio and video signals over vast distances. Communication. Essential in mobile phones, wireless networks, and satellite communications. Near-field communication. Radio frequency identification devices, RFID, used in FOSTAG. Radar. Radio waves are used in radar systems for navigation, air traffic control, weather forecasting, and military applications. Altimeters. Altimeters are instruments used to measure altitude, the height of an object or point in relation to sea level or ground level. They are essential in various fields, particularly in aviation, where they help pilots determine their aircraft's altitude, ensuring safe flight operations. Navigation systems, used in GPS, Global Positioning System, for determining precise locations. Medical applications. Certain radio frequencies are used in magnetic resonance imaging, MRI, for detailed internal body imaging. Remote control, employed in remote-controlled devices, from toys to sophisticated drones. Microwaves. Microwaves are generated using electronic devices called magnetrons. They are absorbed by materials containing polar molecules, especially water. When absorbed, the energy of the microwaves causes the polar molecules to vibrate, producing thermal energy, heat. Cosmic microwave background radiation fills the entire universe and is a clue to the Big Bang. Features. Wavelength and frequency. They typically have wavelengths ranging from 1 meter to 1 millimeter, corresponding to frequencies between 300 MHz, 0.3 GHz, and 300 GHz. Penetration ability. Microwaves can penetrate clouds, glass, plastic, and similar materials, but are reflected by metal and absorbed by water. Non-ionizing radiation. Microwaves are non-ionizing, meaning they don't have enough energy to remove tightly bound electrons or cause cellular damage directly through ionization. Directional propagation. Microwaves can be focused on narrow beams, making them suitable for point-to-point communication. Applications. Microwave ovens, used for cooking and heating food by causing water molecules in the food to vibrate, producing heat. Communication, vital in telecommunications, including mobile phones, satellite communications, and Wi-Fi, due to their ability to carry large amounts of data over long distances. Radar systems, used in radar technology for navigation, air traffic control, weather forecasting, and speed limit enforcement. Medical applications, employed in certain medical treatments, such as diathermy, where microwaves are used to produce deep heating in body tissues for therapeutic purposes. Industrial processing, used in various industrial processes, including drying materials, curing products, and chemical synthesis. Wireless networking, essential in wireless data transmission technologies, including Bluetooth and Wi-Fi. GPS technology, used in Global Positioning System, GPS, devices for navigation and location tracking. Remote sensing, utilized in remote sensing applications for environmental monitoring, Earth observation, and meteorology. Scientific research, used in spectroscopy for studying the properties of molecules. Infrared waves. Infrared waves are invisible to the human eye but can be felt as heat. All objects emit infrared radiation as a function of their temperature. The hotter an object is, the more infrared radiation it emits. Features. Wavelength range. Infrared waves have wavelengths longer than visible light but shorter than microwaves, typically ranging from 700 nanometers, nm, to 1 millimeter, mm. Different bands. Infrared radiation is categorized into near-infrared, near, mid-infrared, near, and far-infrared, FIR, each with unique properties. Absorption and emission. Infrared waves are absorbed and emitted by molecules, particularly those in gases, which vibrate upon absorbing infrared energy. Non-ionizing. They are non-ionizing radiation. Applications. Thermal imaging. Infrared cameras detect heat emitted by objects and are used in night vision equipment, building inspections, and medical diagnostics. Remote controls, commonly used in remote controls for TVs and other electronic devices. LiDAR, it is a remote sensing technology used to measure distances and create precise, three-dimensional information about the shape and surface characteristics of an area. Security and surveillance, used in security systems for motion detection and surveillance, especially in low light conditions. Environmental monitoring, infrared sensing is used for monitoring vegetation health, water bodies, and environmental changes. Telecommunications, some fiber optic cables use infrared light for transmitting data over long distances. Astronomy, it is used to study the relatively cooler objects across the universe, planets, cool stars, nebulae, hence useful to study the birth of these objects. It is also being used by the James Space Webb Telescope to study the origins of the universe. Industrial processes, infrared sensors are used in manufacturing to monitor heat processes and product quality.